Welcome back, guys, to Foundations of Programming, day 17. A question was asked before we started recording was, what does the due date look like for the immersive program coming up here next week on Monday? Your days is going to be Central Time. It's going to be from 8:30 to 5:30. You will come in at 8:30, and then you would have um, stand up, right? So stand up is kind of like a where the team gets together and they talk about like what needs to be worked on for the day or what's going to be covered, right? It's what you typically do in the industry, but we replicate it here to kind of get you used to it. Or if you come in, think about like a morning sync meeting, right, in the military. So that's what it is. But you come in, attendance will be taken, um, and then right afterwards, I think at first it'll be as a group, but once you guys get assigned to, let me rephrase that. The first couple days might be as an entire class, but once you start getting assigned to your groups and working with your group, because you will have your individual group with your own TA assigned to that group to be with you guys all day. Then stand up will be taken care of by the TAs. So they'll like show up and then they'll like do something for the morning. They might cover any questions that you might have. They might cover previous assignments that you've done throughout the like the previous week, right? If there is anything that was given as homework or like any kind of assignment that was assigned throughout the week that you guys are working on throughout the week, you have questions about it. You guys would talk about it as a group, and they would help you guys out. You guys might cover some algorithms early in the morning. They might bring some stuff for you guys, like additional lectures. We try to empower our TAs to ensure that you guys are getting like some additional content of information from a different source, right? It's nice to hear from different people and different ways of teaching, right? We're all a little bit different, and then sometimes it helps to be in this much smaller group. It looks like right now it looks like it's 11 you guys. I thought that was like 13, but it came down to 11. Um, but yeah, it'll start at 8:30. You have stand up from 8:30 to 9. And then once 9 hits, that's when class starts. Breakout rooms are closed. Everyone comes back to the main room. And you guys will have a lecture from 9 to 12 is the lecture time window that we have. 12 is our cutoff time. Doesn't matter if we did not finish talking about what we were supposed to talk about the other time. We cut off and then we try to come back and just finish off whatever we did after lunch. That's rarely a thing. We try not to ever let that happen because we like to respect the afternoon time. So typically, more than likely, we would try to ensure that everything needs to be taught is taught before 12. You might have days where you'll have like 2 hours of lecture, right? It'll be an easy day, and then you'll be working with your group pretty early on, like at 10 or 11. So not every day is the same. Some parts of the curriculum are a lot heavier than others. So you might have some light days, some light weeks, and you will have some very, very heavy weeks where you just feel like you're drowning. So it fluctuates. That'll go on for the majority into your personal projects, but the original timeline is up to 12. You guys go on lunch for an hour and a half, return at 1:30, and at 1:30, you will alternate between either pair programming days or group work. Right, pair programming days. You guys are paired up randomly by somebody. We have like this team generator, or that selects who you're paired with, and then you essentially get together and you code along with each other. And they'll talk to you guys about how that's done. Um, we alternate between days, so like Monday will be like group day, Tuesday will be pair programming day, Wednesday is group day, and so on and so forth. But you'll have from 1:30. Well, technically from 12 if you have a quick lunch, whatever you want to do, right? For lunch is up to you guys. But officially, time wise, from 1:30 to 4:30 is um, everything that you need to do in regards to your assignment time. 4:30 to 5 is team stand down, and then 5 to 5:30 is class stand down. That's gonna be your typical day. Um, And yeah, so I think I mentioned to you guys before, like I think someone asked, like, is there gonna be days where like I'm gonna leave class and I have like so much work to do afterwards? Not necessarily, right? Because you are given the allotted time between 1:30 to 4:30 to work, so you will have time that is just for you guys and working assignments. You can the instructors will typically be there in the classroom in their own breakout rooms. You can ask for help. The TA will be there. You can ask the TA for help. You can ask your friends and your group. But you have like allocated time for you guys to work. Uh, you will probably want to continue working after class over. It tends to happen because it's a lot. It's a lot. Not everyone can just take those 3 hours from 1:30 to 4:30 and call it a day. Like, oh, I'm good. Because it is a lot of curriculum. Does that answer your question, Jason?
Yeah, are they going to send us some kind of like I guess a different Zoom link, I guess when the before the immersive starts, just because I haven't heard of any kind of like immersive Slack room or Zoom link or any correspondence regarding the immersive itself.
Yes, I just got a message right now. They're currently working on it right now. They're getting y'all's GitHub information, and they will be sending out a email tomorrow for your day one. You will be added to an individual Slack channel called Zulu Platoon, right? You'll get added to like 3 or 4 different Slack channels. One for like the main classroom, one for specific for questions. You might have one for like memes, where you guys can just send dumb stuff because everyone always wants to send dumb stuff. It happens. And then you might have a Slack room for your team. But yes, you will be getting added to that. And don't worry about it. It's all taken care of. You'll receive your email eventually. I don't
That's
know
good
why
because
they. Uh
that's good
huh.
because it's like I'm worried about like if I don't hear anything on Friday, it's like hello, like what do I do on Monday?
No, everyone's tracking. We're all tracking you guys. You guys have to take into account that we just graduated our previous cohort, right? And instructors like you don't just go on vacation in the middle of a cohort. Like it's an all day thing. Like Monday to Friday for the entire time that you guys are here. So the only break instructors have are technically the 2 weeks between cohorts. Um, so like there's no much time off, and then like any improvements that we have to make to the course, uh, either has to be done during the cohort, right? Whatever time we can find, or between those 2 weeks. So uh, I know it seems like hey, it's the week prior. I haven't heard anything yet. But trust me, they're well aware of everything's happening. They got it pretty set up. Uh, you guys are the last platoon for our alphabet cycle, right? We're already in Zulu platoon, so we've done it for a while at least. So don't worry, you guys will be taken care of. You'll get a notification tomorrow, I think, at the earliest. Sound good?
Yep.
Awesome. VecTech got approved, so I expect these numbers to be going back up, baby. It's a little thin right now, these groups, but that's okay. It happens. Times change. But all right, without further ado, let's go ahead and jump straight into today's class. It looks like Kenny won't be joining us today. But that's okay. We left off at space complexity. So we were talking about big O notation. I believe we finished everything involving time complexity. Now it's time to talk about space complexity, which is it's fairly similar to time complexity. But we also need to take into account how much space our code is taking, right? Depending on what our code is doing. So the question, what is the time and space complexity of your solution? Right? Is actually asking for two big O values, right? So time complexity, whatever your time complexity of your equation is, not necessarily the same time complexity for your space complexity. Space complexity deals with how many variables slash elements you are storing or keeping track of. Look at the function below. What is the space complexity for this one? Someone take a guess.
I'll just say because there's one variable, or I guess one new variable, one. But I don't know. Hmm.
You are correct. It is O of 1, right? We are only creating one variable, right? The number of variables that we are creating is not growing over time. So it's not O of n, right? It's not linearly. We can still use that same concept. It's only going to create one variable, even with this for loop, right? A new variable is not being created. All we're doing is just, increasing the number of total, right? We're not constantly creating multiple different variables that keep track of like 10, 15, 20 different variables, right? So the space complexity of this is 1. You're correct. Some more examples. What is the space complexity for the following function, right? So here we're creating a list, and it's an empty list. And then we start a for loop, and we're adding the result of whatever is in the parameter of r that's being passed in, multiply by 2, and then adding that to the list. What would you say the space complexity for this would be? Random guess.
I'll just throw O of n out there.
Correct. It is O of n. Right? We mentioned that space complexity deals with how many variables / elements you are storing or keeping track of. We take in a list, right? And what we are doing is we are taking the elements within this list, multiplying them by 2, and then adding it to a new list. So we are now keeping track of the output of each num multiplied by 2, right? So it's going to be O of n being the amount of times that are the amount of elements we are essentially creating and saving into new lists, right? Because we are not actually changing anything to R, but we are actually making new elements and keeping track of these new elements, right? So it is O of n. What about this one?
Is it O of 1?
It is O of 1. We're not creating any new elements or variables or keeping track of anything. All we're doing is printing at constant time. Correct. How about this one?
O1.
It is O of 1. Once again, we are not adding new elements or variables to track. It is constant time. All right. So space complexity tips. Remember broad trends. That's the biggest thing here. What happens to a number of variables / elements being stored or tracked as the input gets really big? Most primitives, booleans, numbers, undefined, null, are all constant time for the most part, right? If a number is a million or if it's 1, it's still constant space, right? So it doesn't matter if your variable is a really big number or a small number. It's still just one variable, right? Strings require O of n space, where n is the string length. This is something that's very interesting here. And the reason for that is because strings are almost handled like lists. Strings are a sequence of characters, right? And you can kind of see this when you try to access the characters in a string, right? You're actually able to access them using an index, right? We're able to iterate to the characters of the string. So even though lists are the same as strings, they're almost treated the same, right? So strings require O of n space because depending on how big the string is, each character increases the size of n. So something to take into consideration.
Does mutability on a variable matter or affect the O of whatever score? Because strings, for example, are non-mutable. They have to be recreated every time you modify them. Is that
Great.
creating another variable?
Well, what happens when you quote unquote create a variable or change a variable, right? And I believe I showed you guys this, right? When you instantiate or declare a variable, like say like green, and it has the text of hello, that is O of n, where n being 4, right? If you try to change the green to hola or something else, that hello, the original greeting you declared, we are no longer keeping track of it. So technically, you didn't create it. You're not keeping track of two elements, two variables, because the moment that you try to recreate a new variable with the same variable name, the original value of that variable is no longer being tracked. It lost the address, which is the variable name that was assigned to it originally. So all you did was took one out and put one in its place. So it's still just one, right?
Yep, that makes sense. Thank you.
Okay, yeah, no problem. Reference types are generally O of n, where n is the length for arrays or the number of keys, right? So list O of n, dictionaries O of n, right? Because you can increase how many they have within their data structure. Time and space complexity of logarithms. So next thing we're talking about is going to be logs. And I'm not always the best at explaining these, so apologize. If you guys have any questions, please stop me, and I'll try my best to explain. We talked about O1, which is constant time.
So, sorry to interrupt real quick, but as far as space complexity, that space complexity tips only talked about O of 1 and O of n. Is that all there is then, or are there other? Can there be worser um, O's and O notations for space complexity?
That's a great question. There could definitely be more. Give me a second. Let me get this going. And I can show you how that can change. And the reason why I didn't cover more in depth of it is because it shares similarities with space time complexity. Big O example.py. Let's say we have a list. Nums is equal to 1, 2, 3. Right? If I said for num and nums, nums dub is equal to empty list. Nums dub dot append num times 2. Right? I take the values in this list, I multiply them by 2, and then I add the contents of the output of that into this new list called num stub. What is the space complexity of this so far?
O of n?
Still O of n. It still takes the same principles as time complexity, where even though we have 3 or 4 lists, like just a single like list with no depth into it, it is still O of n, right? Very similar to like when you have like when you're iterating through a list and you're doing multiple for loops through multiple different lists, but they're not nested. It still stays O of n. Same concept here, right? Although we create another list, it's still just one layer, right? It's going to be O of n being the amount of elements that's going to be stored in num's list. But what if we did something different? What if instead of just doing this, I say something like this: for digit in num, we'll say num stub dot append new list is equal to Might be confusing you here, but maybe I'll explain it a little bit. I loop through nums, right? When I loop through nums, I grab the first iteration, it's going to be 1. And what I do is I loop through the range of 1. I multiply it by 2. I add it to new list. Maybe this is not the best way of doing it. Let's try this. I apologize if it's a little confusing. We'll say something like this, where how can I do this? We'll say something like this, where we grab I say num times 2 and num for num. For num and nums. There you go. Okay, so right now, this is doing the same thing as doing a for loop, looping through the content of everything in here, multiplying it by 2, and then saving it into a new list called num stub, right? We see the output. This num stub is literally the original of nums just multiplied by 2. But let's say instead of doing that, every time I loop through this list, I'm going to create a new list, and this list has the multiplication of it. Let's see what this looks like. What I did here is I created almost like a matrix, right? I took what originally was O of n in space complexity. I made a new list, and within this list, for every single item I had in nums, I created an additional list. And within this additional list, I multiplied it once again. So this is like a nested for loop in a sense, right? The levels is no longer 1. It's 2 levels now. This is a list of lists, and these lists have numbers in there, right? So this no longer is O of n. It now became O of n squared in space complexity, right? Because for every number within nums, I created a new list. And then once again, for every number that's within nums, I created that many new numbers within those new lists I created, therefore making it O of n squared in space complexity. Which is for num and nums, for digit in num, or we could say how could I do it here? This should be the same as this, where I iterate through nums, which is going to be 3 iterations. Every time I iterate through it, I'm going to create a new empty list. I start a nested for loop where I once again loop through nums, grab each item 1, 2, 3, multiply by 2, add it to the new list, and then add that new list to my output. So this should give me the exact same thing of what that list comprehension just did. Does this help, Jason, or did I just confuse you more?
No, I'm good.
You're like,
Just-
that's enough. Please stop it.
No, it's I guess to me it seems like there's a lot of similarities in the O value between time complexity and space complexity, because that's what I would think, because I would think time complexity this would also be, O(n) squared as well.
This would be O then squared, right? In space complexity. Actually, yeah, it would, because we're essentially looping through that list as well. And depending how many times we loop through within both of these for loops, is going to depend how big list the nums list is.
Yeah.
Right. So they share very similarities. That's why I didn't elaborate more on space complexity. Whereas in time complexity, it increases by the amount of iterations you're doing. Very similarly, and you do the same thing with space, but for every new element that you're tracking. Right? This would be different if instead of creating a new thing, I just printed something out. Then it wouldn't be O of n squared in space complexity. It would just be O of n. But because I'm making new items and add them to that new list in this manner to create this matrix, it makes it O of n squared in space complexity. Does that make sense?
Yeah.
All right. All right. Let's go ahead and move forward. You guys hear my kid crying in the background? No? Okay. All right, so logarithms explained. We talked about O of 1, O of n, O of n squared. Now let's talk about O log of n. Where did it go? Yeah, so we talked about the more common ones, complexity is O of 1, O of n, O of n squared. But sometimes big O expressions involve more complex mathematical expressions like O log of n or O n log of n. So what is a log or logarithm? And essentially, it's the opposite of an exponent, right? So look at the exponents. This is kind of what we've been using so far, right? 2 to the power 3 ends up giving you 8, right? Because you multiply 2 by 2, which is 2 to the power 2, right? That gives you 4. But then you multiply that by 2 again, which is 2 to the power 3, and that gives you 8. Well, that can be explained using logs as well, where log base of 2 or log 2 base of 8 is equal to 3. Because if we divide 8 by 2, it's going to take us 3 times to reach, I forgot the term for it, the base of it, right? If you get 8 divided by 2, gives you 4. You get 4 divided by 2, gives you 2. So it took us 3 times to divide it to reach the base of 2, right? Where it's the same as saying 2 to the power 3, we multiply 2 3 times to reach 8. Does this make sense so far? Right, so whereas exponents, it's how many times we have to multiply something. Log is how many times it takes to divide it to reach the base, right? And everything that we're going to be working when it comes to logs, it's going to be all by 2s, right? So you don't have to worry about any of the other ones. 2 is all you'll need. There's a lot of log bases, not just base 2, but for our purposes, we would treat all logs the same. We just care about the big picture. A rough rule of thumb, the logarithm of a number measures the number of times you can divide that number by 2 before you get a value that is less than or equal to 1. You won't always divide cleanly. Look at the number 8 again. Once again, the first iteration, we get 8 and divide it by 2. It gives us 4. Right? That was the first iteration. You get 4 divided by 2, it gives you 2. That's your second iteration. And then you divide by 2, gives you 1. That's your third iteration. So the log of 8 is equal to 3. Why are logs important? Certain search algorithms have logarithmic time complexity. We'll get to these algorithms later in the course. But the way that it works, and the way I like to see it, is like this. And we're going to use TO-draw for this. Let's use a list, for example. We'll call it nums again. We're going to have 1, 2, 3, 4, 5, 6, 7, and 8. Say I'm looking for the number 1. Yeah, we're looking for the number 1 for now. Actually, no, let's not do 1. Let's do 8. I think 8 will make more sense here. We're looking for the number 8. If we did a normal log of n algorithm, what would that look like? What would be an O of n algorithm that can find me 8? Not a trick question. You've seen this.
Well, I mean, it would start from the beginning and go all the way to the end, you know.
Correct.
So,
Exactly.
yeah, it's worst case scenario in this case.
Yes. O of n would end up being something like for num and nums, if num is equal to 8, print founded. This algorithm is an O of n, because worst case scenario is not to loop through the entirety of this list to find it. Right? That's what we were talking about earlier. But let's implement logs in this. If I get this nums list and I cut it in half, right? I can check whether the 8 is in here or in here. This, keep in mind, this is an ordered sequence. I know that it's going from 1 through 8. This is an ordered sequence. This works with ordered sequences. What I can do is I can check the last index for the first half of the list and say, hey, is 8 greater or equal to or less than index 4 on the first part? So I can say something like this, where start is equal to nums and n is equal to nums uh 0, 1, 2, 3. So this has to be 4. 0, 1, 2, 3. But this is up to but not including. So I have to put it to 4. This right here will grab the first part of nums. This will grab the second part of nums. Right? And then I would check. Is 8 greater than index -1 or whatever the end is to start? Well, it's going to grab that forward and say, hey, it is greater. Well, that tells me right off the bat that everything in the first half of nums is not needed. If 8, the number I'm looking for, is greater than the biggest number in here, then everything from the 4 and to the back is useless. I know it's not there. The only thing I have to focus on is now just this. So now I grab that and I split the ends in half and I check once again. Is a greater or less than 6? It's greater. So I no longer need this part. And I grab the last part, split it in 2, and compare it. And it leads me to 8. By doing this algorithm, I was able to cut down my time complexity from O of n to O log of n, which is 3. Right here, worst case scenario would be 8, the length of however this is. Or I think it's 7, actually. Do you see how this works? So, log of n works great. And now it might start making some more sense of why, let me find the graph I like, of why log of n, this is the input size, the bigger the input size, the less computations it does. It works better with the more amount of elements or variables or iterations you're doing. Because the bigger it gets, the more you see the effect of how helpful log of n is. Whereas linearly, it grows as the n grows, right? As n grows for logarithmic algorithms, we actually get faster. But I like to think of this as almost like a divide and conquer method, right? You break this up in half, you divide it in 2s, right? That's what we do base of 2. Because we divide it in 2s, and then we compare from one to the other. And we were able to do 3 iterations to get our answer, whereas an algorithm that's O of n of time complexity can take up to 8 iterations, worst case scenario. Here, worst case scenario, 3 iterations. That's it. Base case scenario, 1 iteration where I cut it in half and it's one of the first ones I check. Make sense? All right.
Is there a log shortcut for building loops in order to implement the step algorithm? Or do you have to just code it out the whole way?
As far as I'm tracking, you're going to have to do something very similar to this. And you're going to have to use it in one of your assignments that we're going to be doing today. But yes, you're going to have to split up yourself. I don't know if the math module has it. That could be a very good question. W3 schools. We can go to Python and see the math module. I have never used it, but I mean, it is there. Why not use it? Math module. Log. I mean, this will return to you the logarithm for it, but it won't do the actual grabbing of your element. And we can, and I'll show you what I mean by that. For example, the question and answer isn't, hey, what's the log of 8, right? That's not the question. That's not why we use this algorithm. The reason why we use the algorithm to begin with is to grab something, to do something, right? I don't care if it takes me 3 steps. That's cool. I still don't have my answer. Make sense?
Sure. Really, I guess my question was poorly worded. Is there a Python or maybe a JavaScript method that you feed it a number and it runs this type of algorithm against a list or a set or a tuple?
So you're saying if I have, for example, let's say math dot log 2, right? Let's just say it exists. And I give it nums and
And then
or
feed it
something.
an array or a list.
If
And
I
it would,
give it like 3 and then I give it nums, and it's
Mhm.
gonna return to me 8. Or like the index of 8, is that what you're referring to?
Yeah.
No.
Okay.
Because it won't know what number it is. Right? I guess this is like a mathematical equation of what is the log of the length of nums. But we're not necessarily looking for how many times it's going to take to find something worst case scenario. We're looking to grab an item from the list. I don't believe anything like that exists. You can probably create a function to do that, but you would still have to hard code this portion. Make sense?
Yeah.
I feel like it'll make more sense once you actually start doing it, and you'll see what I mean. Maybe I'm not doing the best at explaining it.
Oh no, you're explaining it just fine. I understand the concept. I'm
Okay,
just
thank
wondering
you.
if, because it's such a common algorithm to run against a data set, if there was a shorter way to do it.
Yeah, I've never seen it. No, but that is pretty cool. So why are logs important? I think we talked about this. Some of the more efficient, better algorithms involve logarithms, most notably binary search, which is a common search algorithm used in technical interviews. This is the name, I believe, is what it's called now, of how to like what I just did there, where I split up into twos, got one search of the other. It's very common for that. Um, this works with but what am I trying to say? It works for sorted arrays, right? If you try doing that with something that's not sorted, you're just wasting your time. You might as well just loop through the whole thing, right? So it works for sorted data structures. Recursion at times involves logarithmic space complexity. We'll talk about that at a different time. If you want to know a lot more about logarithm, that book I sent you guys on Slack does a great way of explaining it. Great way. And I believe they use something very similar to this, but I think what they use is like pieces of land. They show you a picture of land and tell you, if you're looking for something, there's a way to cut it out from one side and then just focus on the other. But they do a great way of explaining, so definitely check it out. But those are the three most common ones. The other ones we won't be touching. You'll be talking more about them in the immersive program. Especially this one right here. This one's a little weird one. Worst case scenario of any kind of complexity. But the three ones that we're talking about is going to be, or the four is going to be O of 1, O of n, O of n squared, and log of n. That's what we were focusing on with this lecture. Once again, the same graph that you've been seeing nonstop. Dictionaries and lists in terms of big O. Dictionaries, insertion. Inserting into a dictionary is O of 1, right? Same as removal. Because all you have to do is assign it a key and value. You don't have to shift anything around because it's not in ordered sequence. Dictionaries are an unordered data structure. So inserting something into it, O of 1, it's constant. Removing something, same concept. You grab the item using a key and just delete it. So O of 1. Accessing, O of 1, once again, you're using the key to locate it. You don't have to search for it. Searching a dictionary, now that becomes O of n, right? If you recall, if you had dict1 is equal to, you had your dictionary, and then you said for key in dict1.keys, this returns to you a list of keys, if you remember. So this essentially starts a for loop. Therefore, searching in this manner is O of n. So dot keys is O of n. Values, items, O of n, all O of n. For lists, insertion at the end of a list is O of 1. because you don't have to guess where it's at. Right? You just go to the very back of the end of it. But inserting it at the beginning becomes O of n. Right? Inserting the n is O of 1, but inserting it at the beginning, it's O of n. Why?
Actually, I mean, I would have thought that'd be O of n because it would matter how big, the list would be if you know exactly where it's going, right at the very first slot or first into zero index.
You have nums 1, 2, 3, 4, 5. If I want to add something to the end of this, I don't have to guess index, right? I can literally just say nums dot append, number, whatever it may be. That will automatically put at the very end. Nothing is affected by doing that, right? But
You have to
I wanna
shift if you use an insert, right?
there you go. That's exactly what's happening, Tim. If
Gotta
I
shift
try,
because you gotta shift everything. That's why it's O of n. Okay.
correct, I think the command insert. If I insert into index 0 a number, all this has to move to the right one index over. So it becomes O of n being the amount of items within this list. So every single item shifts over at least once. So inserting it at the beginning now becomes O of n. Removal of the n, O of 1, does not impact anything. Remove the beginning, O of n, same concept. If you remove something, everything has to shift to the left. Accessing an item in a list by index, O of 1. Right? O of 1 because you're using the index, right? Accessing with the index, you go straight to the index. But if you search, not knowing what the index of the item you're looking for is, and you start a for loop to iterate through it, that's O of n. Sorting, using the sort methods, right? That's n log of n. That's actually not a very effective method either. But n log of n, we're not going to go into n log of n. That's out of scope from here. Slicing, O of n, right? If you're trying to grab a section of the list, it's going to depend how big of a section you're trying to grab. Filter, reduce, map, these higher level functions, higher order functions are O of n. When you filter through a list, you go through every single item. When you reduce, when you map through every single item. That for each method in JavaScript, O of n. Any questions?
Yeah, actually one.
Yes.
I would presume be O of n, but if you insert into the middle of a list, is it still O of n because the number of items in that list is unknown, and just because you're putting it somewhere in between the first and the end, you still have to shift an unknown number?
Correct. O of n. Thank you for that question. All right, common problem-solving patterns. This is the next part of lesson 11. We have multiple, right? There's a lot of patterns out there, a lot of different algorithms. These are the more basic ones that you should know starting off, which will actually help you solve a lot of the more common problems, right? We will cover these 4 patterns, but there are many more. Some more advanced than the ones we have here. And this will just kind of get you started, get your feet wet on the different types of algorithms out there, right? Up to this point, you probably might have guessed that you actually don't just randomly engage at a problem. There's actually tricks to how you solve things, right? Those coding challenges you guys did, there is probably some kind of pattern that you could have administered that would have solved the coding challenge. I don't know what they were because I haven't done them in a long time. I know they changed the questions that are given to you guys. Now it's down to 3, but there's probably some kind of trick that you guys didn't know at the time. But most coding challenges or questions there's usually a trick to it of how you can approach them. It's kind of like chess, right? If you remember playing chess as a kid, you probably just started moving pieces. You knew how the pieces move, but you kind of just winged it. And then you come to find out there's actually like moves or plays that they can do in chess depending on the positions of the board, right? Of where the pieces are at. There are legit moves out there. There's a whole playbook. That's kind of what coding challenges are. Sure, you can probably solve it if you kind of force your code in there and you start looping through everything and checking things. There's probably a way of doing it. But there's actual plays to use, right? And this is what we're going to be talking about. We're going to be talking about your playbook and adding some plays into that playbook. Now, I don't expect you to be subject matter experts on these by the end of this. This is to expose you to them. Even me and anybody else, you can ask anybody in coding. My friends who are senior software developers. I got a buddy of mine who works at Citibank. He is looking for jobs. Guess what he's doing? He is grinding leak code and having to look up these algorithms. Because that's something that you do regularly in the workforce. Computer science, data structures, data algorithms, they're a skill of your own, right? Just because you know how to make a website does not mean you know specific algorithms, right? These are skills of their own, so don't feel bad if you don't get them right off the bat. It takes a bit to kind of really understand it. I am very visual learner, so I always had to look up like, someone showing me this on some kind of like drawing board, like this is what this is doing, and yada yada. Oh, that makes sense now. But the first one we're going to talk about is going to be frequency counter, right? This pattern uses dictionaries to collect values and frequencies of elements. This pattern can help you avoid the need for nested loops or a O of n squared operation with arrays or strings. We'll just take a quick look at this and then we'll jump into the problem. Here we have a list of different numbers from 16 to 19. They're in order, right? And these are things that you guys need to be taking into account. When you guys look at your problems and you engage into some kind of challenge, you got to look at your data structures, data types. What are you working with? Is it a list? Is it a dictionary? If it is a list, what is the data types that they have? Are they just all strings? Are there zeros? Are there any none values? If there's numbers, are they in order? Are there duplicates? Right? All these little clues will give you an idea of how to approach your problem. So here we have a list, and right off the bat, I can see that this is, for one, it's integers. They are in order, and there are duplicates. They created an empty dictionary called frequency, right? And they use this to keep track of the numbers that have appeared and how many times they've appeared. They then start a for loop for items in new list to iterate through the list of numbers. And as they iterate through them, they add the items into the frequency dictionary where they call the dot count method on their items to get how many times it appears. And then, keep in mind, this might not be the best example. I'm just showing you how frequency counter works, but this is not necessarily the most efficient way of doing this algorithm, which you can probably already see why. The next time they loop through the key value pairs of items and they print out the string of count frequency and the dictionary. So maybe not the most efficient code. Why is this not efficient?
It could be done in a single loop by checking if it exists in the dictionary. If not, adding a 1, and if so, just adding 1 to that existing number in the value, and then printing the whole thing.
Yeah, and this, so right now, what you're saying is this is not a single loop? Why or why not?
So efficiency-wise, it's two separate loops. They're not nested. So
Are they nested?
no, they're not.
What about count? What is count doing?
Yeah, I guess count is a loop, right? It just goes through and
Yeah,
counts each item.
it's a built-in method. But as you already know, that some of these methods, they're not just magic. They're doing something under the hood. There's some kind of programming that was made, right, in some module that you have somewhere in like the code of your Python that handles this. It's not just magic. Dot count, what it actually does, it starts another for loop. And it goes through the new list. It takes the item that's being passed within the parameters, and it looks for that throughout the entire list, and it returns you how many times it found it. So actually, this is O of n squared. So, like I said, it's not efficient. I see what they try to do here. They try to implement this frequency counter, but to avoid a nested for loop. But they just ended up making a nested for loop. Anyways, it's probably not the best way of doing this. But yes, Tim.
Sorry. Just random question. Do other things like if you instead of doing that, you just found the -1 indices of a list and then subtract 1 from it, wouldn't that get you the same the count as well?
I'm confused at where you're getting at. Can you
Okay, so
explain that in a different manner?
if you just for example, print, you have that list, right? And you say print new list index -1, that should get you the last item in that list, and then -1 more. No, never, it didn't start at 1. Disregard. You'd have to subtract the first value also. I'm rambling. Don't worry about it.
Okay. Okay, it's fine. But yeah, so this is not the most efficient way of doing it, but I still show you this so you can kind of see what they were trying to apply here, and I want you guys to do it better. All right, so student practice frequency counter.py. It is now in lesson 12. So you can go ahead and open that up. There should be nothing there. It should be empty, and there should be a readme. You're going to write a function called same, which accepts 2 lists. The function should return true if every value in the list has its corresponding value squared in the second list. Their frequency values must be the same. You have the test cases here. Let me go ahead and copy and paste these. So you already have test cases. All you have to do is define the function and then run this. And we can see here an example of what it should happen. The first one returns true. Well, let's see why. It takes 2 lists, 1, 2, 3, and a second list that's 4, 1, 9. And once again, it needs to return true or false. It's going to return true if every value in the first list, which is 1, 2, 3, has its corresponding value squared in the second list. So here we have 1. Does 1 exist in the other list squared? Well, 1 times 1 is 1. So it is here. So that takes care of that. The next item is 2. 2 times 2 is 4, right? That's squared. So it exists. And 3 squared, 3 times 3 is 9, and it exists here. So therefore, this returns true. This one returns false because 2 squared does not exist in the second list. And this one also returns false because of the frequency, right? 1 squared, I find it here. We then have 2 squared, it's here. Then we have 1 again, but we have already accounted for the 1 squared once. There's not another 1 in here. So because there's not the same frequency, that's an issue. With that knowledge, go ahead and give this a try. Time is 6:31. I want you guys to work from 6:30 to how much should we take? 15 or 20 minutes? Thoughts?
You can start with 15.
All right, let's go with 15. Let's come back at, let's say 6:30, 6:47, then go on a 10-minute break. So we'll come back at 6:57. Okay? Because it's already 6:30. I'll see you guys in. Let's go ahead and come back. Tim, how does length affect space efficiency? I'm assuming you're talking about space complexity.
Yes, apologies.
It's okay. Can it be mitigated by something like Oven? Space or time? Which one are you referring to?
Space. I would presume len would probably be a loop.
Yes, in time complexity wise, length is a for loop. The list is O of n, n being how many items you have in that the list.
But
Right,
if
for
you did
space.
if you did it the way that I put in the chat, then it would only be searching one possible instance one time.
Index of whatever you have list for -1. Trying to find why are you trying to find the index of something if you already have I guess because you're
Because I wanted to get the length of the list
I see what you're okay. I
without
see what you
using
mean.
len.
Well, length won't affect your space complexity.
Only time.
Technically, if it's not nested.
Okay. It was just curious.
Yeah. The length won't affect your space complexity. You're not keeping track of any new variable. Like you would if you had like a bunch of dictionaries or lists or whatever nested within each other. So it would still be O of n. So the length will not change the space complexity. It would change only time complexity if you are checking length every single time within an iteration of a list, right? Which is like will make it O of n squared. But no big change there. Okay. Can I make the assumption here that one of you guys were able to complete it or no?
Yeah, I completed it.
Yeah, I did too.
I want to see Jason's. Like Tim always presents. Let's see Jason. Let's say that Jason doesn't demonstrate, but Tim always jumps the gun and tries to hop in there, which is good. I like the initiative. Let's get it. We can see your screen, Jason,
Okay.
whenever you
Okay.
are.
Okay. You hear me?
Yes, we can.
Okay. So the first thing I did was I noticed, like in the second example, that the lengths of both lists were not the same. So if that's true, if they're not the same, then you could automatically, it's automatically false. Because you can't have this, you obviously wouldn't have the same frequency, if you had a different number and, what the length of list one versus the length of the list two.
Yes.
Okay, and then I pretty much just did a for loop, so for, num in list one, if num squared is not in list two, you'd automatically return false. But then on each iteration, that was true, I would remove num from list one and then num squared from list two, and then it would go back through the iteration. So as long as it makes it all the way through the iteration, the length of the list, it would eventually return true.
Okay. It works. I like it. Now, here's me just picking at you. One, I don't want to see if you guys complete it. I'm glad you're able to solve it, but it's
Yeah,
not the solving it that is I'm trying to see here. You want to implement dictionaries, the frequency counter, right? The whole purpose of this exercise is to see how you can take something that's O of n squared and make it O of n using dictionaries, right? So right now, the time complexity on your assignment, which I'm glad you're able to do it. You understand it. That's good. You solved it. This is O of n squared. Why?
Nested for loop.
That nested for loop. Line 8, when you say if num to the power of 2 is not in list 2, that not in, we call it a membership check. We're checking if something exists in something else. How that works is a for loop under the hood. So that made a nested for loop, therefore increasing your time complexity to O of n squared. The intent is to keep yourself from doing that, right? And using the dictionary the ability of being able to access dictionaries with constant time, thanks to the key value pairs, to get away from the time complexity of O(n) squared. Make sense?
Yeah.
Not picking on you. Good. I'm glad you're able to solve it, right? You probably 4 weeks ago, you probably would have been lost in this problem. I'm not even gonna lie to you. So I can see you're making great improvements, but not exactly what I'm looking for. But thank you though.
Okay, I'll be interested to see Tim's solution then, so I can learn.
And you know what? You're not gonna be the only person that did it this way. I guarantee you, if someone else tries this before seeing the solution, they probably do the same way too. You're not the first, and you're not the last person that's gonna do this. You trust me. But let's see, Tim. Were you able to do it the way that it should be, or did you do it like Jason?
I didn't do it exactly like Jason, but I probably have a nested for loop because I relied on a dictionary get call, which is probably a nested for loop.
Is it? Let me look it up.
Ignore everything down here. I was just messing with lists because I was bored.
Because it's searching. Would it be considered searching?
So I created a dictionary. I did a quick loop to throw all of the values of list 2, which is the squared values that we're checking against, into that dictionary, and then ended that for loop, and then ran another one using if inside that dictionary exists a key that is the value of the first each iteration of the list 1 squared, already equal to 1 because we set it to 1 in the first for loop. Then add another one, and then if it finds that value either 2 or 0, meaning it wasn't found, then return false.
Okay. Does this work?
Mhm.
This is O(n). Dot-get, I just looked it up. I was pretty sure, I was confident it wasn't O(n). But O(1) is constant time. I'm sorry, dot-get methods are constant time in dictionaries.
Great.
Um,
Because it just does the error checking for you, probably. Instead of looping through everything, it just looks to see if it exists. Basically, instead of looping it through everything, it just checks against the dictionary. If it doesn't exist, returns whatever you defined it, in this case, 0.
correct. It attempts to access it by the key. And if it doesn't, it returns to you something anyways.
Okay.
So it does the error handling. There is the ability of it giving you an O(n) time complexity. And I see here, in rare situations, a hash collision can occur, meaning multiple keys may map to the same, I guess, bucket, right? Or whatever, like same value. In such cases, you might get O(n), right? That could be the worst case solution. But just make sure that you don't have repeating keys. I mean, you don't want to have repeating keys, right? Or something like that. And they shouldn't. I don't even know how that can happen. I've never seen that happen, but from what it looks like, average wise, yeah, it typically has an O(1) of constant time. But I mean, so far it looks like it's O(n). I'm sorry, O(1). No, O(n).
Hovan, because non-nested for loops.
Good stuff. It's pretty cool because I usually see other people do this differently. You guys both did it in a way I have not seen. So pretty cool. All right, let's go ahead and move on with the remainder of our lecture. So a not so great solution, right? We start some kind of a check, right, where we compare the lengths of our list to see if they match. Obviously, if they don't have the same length, that means one of them is not a period, and that they're missing the frequency. So right off the bat, we check the length and return false. For I in range, they do a for loop in the length of the first list. They then grab the value of the key for the items on that list. I'm sorry, not the key, the index. So they grab the index. They're essentially looping through the entirety of list 1, squaring the numbers at each specific index, saving it to a variable, and then doing the same thing Jason did. If squared num not in list 2, right? They're doing a membership check. The not in it creates a nested for loop, right? So they did literally what he did, and then they use an index method even worse. This is probably O of n cubed, right? Because this index method, oh no, it's not. It's O of n squared still because it's not nested within this if check. So O of n squared, but index it does a for loop, right? It grabs the item you're trying to pass in as an argument. It loops through the list that's being called on, and it's going to return to the index that it finds it on. That's O of n, right? N being the worst case scenario is probably the last item on this list, and that's to loop through every single item to find the index. So yeah, not so great solution. Jason was probably trying to cheat, and he saw the slide. He's like, "Oh, is it?"
I actually didn't see the slide.
Okay, you're good. You're good.
Well, no, I don't want to cheat because cheating you're just hurting yourself when you're cheating. So no, I didn't even see
Absolutely.
the slide.
Don't cheat yourself. Treat yourself. All right. Next one is a better solution. The in operator in Python is O1 for dictionaries, but O of n for lists. Right. So here is kind of that disclaimer that I mentioned about earlier. This is usually the way I see it, and usually the way I code it out too. Whenever someone doesn't finish it and I have to walk through it, I'll code it very similar to this. Once again, they check the length of the list. They create two different lists, one being the frequency for the first one and one being the frequency for the second one. They started for loop. And then every time they encounter an item in the first list that is already in list one frequency, they increase the count. If they have not encountered it yet, they add it to the dictionary. And they do that for both, right? Afterwards, once both list one and list two dictionaries have been filled up with their respective numbers and frequency for each number, then they then do another for loop. They loop through the first dictionary of list one, right? This returns the key, right? For key in list one frequency. With that key, they square it and check if it's not in the list two dictionary. The in operator in a dictionary is constant time. In a list, it's O of n. So because now they're not essentially lists, they're dictionaries, they can actually use a not in operator here. And we know that list two has to be the squared version of list one. The keys were used to create the key value pairs, right? The values was the frequency of how many times these numbers appeared. So that means that they could just grab the key, square it, and see if any of the keys in list two match it, and they're able to reset outcome. If at any point the one key in list one frequency does not equal the squared version in the list two frequency, then that means it doesn't exist, right? So exactly what you guys were doing, well, Tim, but in a different manner, right? A little bit more code. And then it kind of brings the question, right? Well, which one is better, Roger? Right? If the time complexity is the same and the space complexity is probably the same, then which one's better? Well, then that comes down to readability. What can you read better? Does this make more sense to you than Tim's does? Or does Tim's makes more sense this one? And that's how you weigh which code is better. Cool?
I mean, I guess I'd say this code looks kind of repetitive, even if it is more efficient.
It does look a little bit more confusing, right? It's significantly like more lines. There's like three different for loops. The names look very similar to each other, so it can be very easy to get confused. So I mean, I guess it would depend on the eye of the beholder. You know, like what's actually more confusing to you, Tim, might be more simpler to me. But at the end of the day, it's not an individual thing. It's about the team, right? How does your team think about your code? Do they think it's easy to read? Can they come back here and debug it? Can they understand it? Can they build off of this? All right, so things to take into account. There's no specifically like right or wrong answer unless we're talking about time and space complexity. When it comes to readability, There are some common practices, but sometimes something might be more confusing for others. All right, anagrams.py. You guys probably did something like this coming in. The anagrams assignment. Let's look at it. This is something else. Anagrams.py. Let's get. Given two strings, write a function that determines if the second string is an anagram in the first. An anagram is a word, phrase, or name formed by rearranging the letters of another, such as cinema, formed from Iceman. Right? Keep in mind, this is not, I believe it's called a palindrome, is what I'm thinking about. This is not a palindrome, right? Where you reverse the string and it should match the same or something similar to that, right? This is just saying if all the words on the left, if they are rearranged, can they equal the word on the right? And we see here the first one, we have AAZ and ZZA. This is not an anagram because there's two A's on the left, but one A on the right, while there's one Z on the left and two Z's on the right. The second one is true because every single letter on the left side appears on the right the same amount of times. So, an anagram is a word, phrase, or name formed by rearranging the letters of another, such as cinema formed from Iceman. Right? Do I have any questions about this assignment? We'll take 10 minutes for this one. Give it a try. All right, welcome back, guys. Let's take 10 minutes time for this one. And one thing that I think I might have not read over at the very end says give the time and space complexity of your solution as well. So I'm going to want that once you're done explaining your solution. But if you don't mind sharing your screen, Tim, what you got going on?
What if I do mind? No, I'm just kidding. Hold on.
I've never been in this situation before.
Yeah, I think I got. I think I got it. I'm just afraid now.
Okay. So it was very similar to the last challenge, except well, just minor tweaks. So this time, instead of creating one dictionary, I created two, one for each string, and I immediately started out saying if the lengths of the strings are not equal, then it can't be an anagram, so return false. Ignore that. Don't actually need it. And then I created a for loop with the range of the length of string 1 because it's equal to string 2, so it doesn't really matter. And I said if the current character that we're checking in string 1 is in string 1 dictionary, then string 1 dictionary that's supposed to be 2, wasn't it? No, that's right. Then add that character as a key with the value of 1, or add 1 to the value in that key. That's right. Otherwise, that key equals 1. So I basically just populated string 1 dictionary. Then I did the same thing for string 2. So each dictionary is just the letter for each letter in the given string, and then the number of times that it occurs. Then I ended that for loop and created another one and ran through all the keys in string 1 dictionary and said, if string 2 dot get keys key does not equal string 1 dot get keys for the keys, but I created a different else case. One is 0, one is none. So if they're not equal, then return false because there's no possibility it's an anagram. I created different false cases because otherwise they could both come back as false, not being found, and it would return true when it should be false.
Correct. That's pretty good. Yeah.
So I was about to say, so my solution was actually very similar. The only thing I had was at the end, I just found out if dict1 equals dict2, return true, else return false, seemed to work.
Yeah,
That's probably better.
that is a good way of doing it, and not one way that I usually do because I forget that you can do that. Because you normally wouldn't think like, I mean, how would I compare these? Have you tried comparing two dictionaries that are different?
Well, I looked it up actually. I just
Okay,
said, yeah, I basically just typed in Google like, Python methods or checking if Pythons are equals and dict1 equals dict2, It's like that
okay,
easy. Okay, I'm gonna go for it.
yeah, no, absolutely. By all means, that's a pretty good way of approaching it. Yeah, no, uh, no judgment here. That's pretty good. And now you know, and now I'm confident doing that myself as well. Okay, that was pretty good. Its time is 7:31. Let's go on our last 10-minute break. When we come back, we'll tackle the last two problems, and then we will call it a day. I'll see you guys soon. And get started. Welcome back, everybody. So we just covered frequency, right? So frequency concert using two different examples. The next one we're going to talk about is going to be multiple pointers pattern, right? Multiple pointers pattern. This pattern consists of creating two pointers that correspond to an index in your list and moves towards either the beginning and or middle of the string slash list based on a certain condition. It's a very efficient way of solving problems with minimal space complexity. Space complexity. Well, how does that work? Let's go back to TOJAW, my favorite platform. And I'm going to go ahead and have my list here.
You're not sharing your screen.
Oh, my apologies. Well, here's what I was showing when I was talking. My apologies. Um, you can kind of see a small diagram here. You have a list here, right, of different numbers. They have two pointers, and one pointer starts at the beginning and one at the end. And we see the second part of the picture. We have the pointer is now shifted to a different part of the list, and we'll see how that works. We have a list here: 1, 2, 3, 4, 5. And the way that you would do it is you create a pointer. You can call it whatever you want. You can call it start. You can call it pointer 1. Whatever helps you understand it. We'll use P1 and P2 for now, but you're more than welcome to use start and end. P1 will be my first pointer. And I'm going to set this to the start of my list. So I'm going to say index 0 of nums. I then create my second pointer, which will be the last index of my list, right? So by creating these, and actually, let me put these in two different texts. Oh, P1 is equal to nums -1. P2, my bad. These variables we created point to two different parts of my list. And the way that this works is you do something very similar to this, where you start a loop. Usually, you want to start a while loop. Start a while loop, right? And you will say something like while one of these pointers does not equal something, you want to continue this loop. Usually, an example we're going to use is while my start pointer does not equal the last index, I want to run this this while loop. So I'll say, well, P1 is less than nums index 1 or index -1, which should be this. Or it could be something like, well, it's less than the length of nums. Is another way of doing it. I want to run the following code. So this will keep running until P1 reaches the condition where it's equal to the length of nums. So for us to stop this while loop, our pointer, our starting pointer, needs to increase in size to the point where it exceeds the length of what my list is. So when this first starts off, P1 is E0, right? Because we're at the 0 index. Actually, it's going to be not necessarily num0. We say 0 because we're referring to the start, not the number assigned to the index. This should be length of nums. My apologies. -1. Something like that. Right? That way, if there's 5 items here, this index is 4. We want to point to that index, not the number assigned to the index. We want to point to the index, right? So I do apologize for that. I might have started us off a little bit wrong, but now we're back on track. We want to find the start and end points of our index. So we have index 0 and index 4, right? That's what P1 and P2 are. At some point, P1 needs to equal 5, so it stops iterating through this. Let's say we're trying to find the smallest sum or the greatest sum within our list. Like what two numbers here, when added up, are equal to the greatest sum in this list. For example, 1 plus 2 is 3. That's not the greatest sum because we could probably get 4 and 5, which will be 9. That's probably the best sum that we are looking for. Right? But we don't know that. We don't know what's in this list. But we're trying to find this combination. So when we start off, we'll say something like this. If P1, or actually nums P1, plus nums P2 is greater than sum, and we can track like a variable called sum here that we can set it to 0 to keep track of what our greatest sum is. And as we find bigger sums within our iteration, we want to override this current one. So we start off and we're going to check what is the sum of the two numbers we're pointing at. Right now I'm pointing at 1 and I'm pointing at 5, which gives me 6. So this is going to be true. So the addition of the item in index 0 and the item in index 4 ends up being greater than sum. So sum should equal nums P1 plus nums P2. Therefore, changing what our current sum is, and we've now found something that's bigger, right? And if we found something, what needs to happen is we need to shift one of these. Well, this loop needs to run until P1 reaches the end. But we still have a bunch of combinations that the number 1 needs to check. We check 1 plus 5. What about 1 plus 4? So we can't move on until we check that. So after we check the first number, we say P2 minus equals 1. So it brings it to 4. But what if we encounter a situation where P2 does not equal something greater than sum? But we also have to say else P2 minus equal 1. Right? Or elif nums P1 plus nums P2 is less than sum, then I want you to subtract what P2 is. And we can say if P2 is equal to P1, then I want to shift P1 to the right. P1 plus equals 1. And then we would bring P2 to start again to the end. Right? Something very similar to that. P2 is equal to the length of the nums. Now, this is not perfect. I need to go back and fix the logic of this. we might want to put this at the end. But essentially what's happening here is we check, hey, is 1 plus 5 greater than sum? If so, then change what sum is, and then decrease whatever P2 is. Then we check 1 and 4. Then we check 1 and 3. Then we'll check 1 and 2. And then at some point, P2 is going to equal the same as P1. When it gets to that point, that means we check all the possible combinations that P1 can have with whatever P2 is. Therefore, we then increase P2 to the next one, and we reset P2 to the end. And then we check this combination, 2 plus 5, 2 plus 4, 2 plus 3. P2 ends up being the same as P1 eventually. We reset P2, increase P1, and restart that loop. And eventually, it increases past the length of what nums is, and it stops the while loop. By the end of this while loop, we can figure out whatever sum is. Whatever ends up being the sum, that was the biggest one, right? Because as we've been iterating through here, we found which one was bigger, and we've updated it as such. We've gone through every possible situation using these pointers. Does this make sense somewhat? Yes, no, maybe so.
In this case, does it matter? Do the numbers have to be sorted?
No, they do not need to be sorted, not at all. That's actually a good situation when you can use this algorithm if they're not sorted, right? It does not matter if they're sorted because you're going to check all these regardless. It actually works better if they're not sorted.
Because like I guess if they're sorted, then it's kind of like worst case scenario. It's going to take every iteration possible to get.
I
to
mean, if
the
they're
end.
sorted, if you know they're sorted, you
Yeah.
just get the last two indexes and add them together. You know what I'm saying? So
Yeah.
this actually is specifically for those that are not sorted,
Yeah.
right? Maybe if I would have done like five, that would have made a little bit more sense. But yeah, you want to look for this works better with stuff that's not sorted. Because if it was sorted, then you just get index -1, index -2, add those up, and call it a day, right? But yeah, it works better this way. Maybe that was a point of confusion, so I do apologize if I didn't clarify that. But yeah, so you use these pointers to be able to grab every single item and check the some kind of logic between them, and then shift them as you're done checking them. With that little explanation in mind, let's look at multiple pointers.py. Write a function called sum0, which accepts a sorted list of integers. The function should find the first pair where the sum is 0. Return a list that includes both values that sum to 0 or -1 if a pair does not exist. Right? So here, we have a list from -3 to +3. And it returns a list with the integers of -3 and 3, because when you add these together, it's equal to 0. You see the same thing here on the second one, but the last two, we get -1, because no possible combination here gave us the sum of 0. Therefore, we return -1 instead of a list. So using two pointers, solve this problem. We'll take 15 minutes for this one. Time is 7:53. Let's go ahead and come back at 8:07. 8:08, my bad. Recording. Okay.
I was about to say, sorry, I was about to say real quick, I was about to like enter into like two different while loops, which probably isn't the most efficient thing to figure this out.
It's not. Let's see. Let's go ahead and define sum0. And it's gonna take in a list. And with this list, we need to iterate through it, find which one of these numbers, when added together, is equal to 0. So we're going to say start is equal to 0, and n is equal to the length of list 1 minus 1. So this gives us the last index, and this is for the first index. These two are going to be our pointers. Next, with our pointers established, we're going to start a while loop. We're going to say while start is less than the length of list 1, then I want to do the following. And we might want to say -1, because at one point, if, let's see, this list is 1, 2, 3, 4, 5, 6, 7, but the last item is index 6. And if pointer 1 is index 6 and also the end pointer is index 6, it's going to try to add these together. So we might want to reduce it to -1 to not take this last index into account. So when it gets to this, it stops the for loop. I think we want -1 for that, just to ensure that we don't add 3 plus 3 or 99 plus 99. You see, I was kind of working on this, and I saw it earlier. It gave me 99 and 99. So we're going to do -1. Now, let's give it a try. We're going to say, if list 1 at index start plus list 2, or sorry, list 1 at index end is equal to 0, then I want to return a list with list 1 index start, list 1 index end. Right? Or to not continue repeating this, we can say sum is equal to list 1 start plus list 1 end, and we can use that instead. If sum is equal to 0. There we go. If it's not, then what we should do, if current sum if sum is less than 0, then something has to happen here. Well, let's see. This is an ordered sequence of integers, right? Let's use this one for example. When I add 99 plus -10, what does it give me? 89, right? It'll give me 89. That's significantly higher than 0, right? And because this is an ordered sequence, if I want to get a smaller number, because obviously the combination of this index and this index is way too high, that means I need a smaller combination of numbers. But if I move my start to the right, and I do -5 plus 99, this gives me 94, which is a much higher number than I got originally. So it makes more sense that instead of moving my left pointer, I want to move my right pointer to the left. And now 87 plus -10 gives me 77. It's smaller than it was before. I need to keep bringing this number smaller until it is equal to 0. If it gets to something less than 0, for example, if I add -10 and -5, that gives me -5. Right? That is a lot smaller than 0. So that means I have to increase the numbers that I'm adding together. So I want to check this sum. If sum is greater than 0, that means the combination of numbers I'm using is way too high. So I need to move my right pointer to the left to decrease the size of the numbers I'm adding up together. So then I would say n minus equals 1. If it's not greater and is not equal to it, then more than likely it's less than. So I have to say start plus equals 1. So I have to move my left pointer to the right. Make sense? And then what this is going to do, so far it's going to work, but there's an issue here. And I think it's how we're doing this while loop. Right now, this while loop is going to keep running until my pointer reaches the end. But I don't necessarily always want to do that. Right? The example I gave you is not the only way of doing the multiple pointers. It all depends on what type of data structure we're working with. Right now, no matter what happens, because this is an order list, the bigger my start gets, the bigger of a sum I'm going to get. And that's not ideal. Right? No matter what happens, if this combination of numbers, 99 plus negative 10, is greater than 0, if I move my negative 10 to negative 5, this gives me a much bigger sum. This gives me 94. This gives me 99. This gives me 100, 103, 104, and so on and so forth. You see how that works? So it makes no sense for me to use the start pointer to keep track of when to end. What I think makes more sense is to say while start is less than end. Let's use these for example. We're going to run this for loop until start and end are not greater than each other. Now let's see it. Negative 10 and negative 9. We add it together. Gives me 89. Well, sum is greater than 0. So I'm going to move my n to 87. It goes back around the while loop. Negative 10 plus 87 gives me 77. It's still greater than 0. So we move 87 to the left. Negative 10 plus 5. That gives me negative 5. Still not what I wanted. Now it's less than 0. So I need to move my left pointer to the right. Now we have negative 5 and negative 5. Now it's equal to itself and it returns this. So it never got to the point where start is greater than end because we got to the point where sum was equal to 0. So we return here. This will stop this while loop. Well, what happens in the event that we don't encounter sum is equal to 0? Well, that's when we can use these examples. Positive 3 plus negative 2 gives me negative 1. That's less than 0. So I'm going to increase my start by 1. So it brings me to 0 and 3. 0 plus 3 is 3. That's greater. So I subtract negative n by 1. Now it gives me 0 and 1. I add these together. It gives me 1. It's greater than sum. So I move my end to the left. So now I have my start and end are both equal to 0. At no point did I encounter a sum of numbers that gives me 0. But now I encounter the condition set on my while loop and it stops. So what that tells me is I never got to a sum where two numbers were giving me the equal of 0. And I already went through everything within my while loop. Start and end are either equal to itself or less than. We try to add 0 and 0. So we can put this like not equal to maybe, and would work maybe. I don't know. But it'll try to add 0 and 0. We'll get 0, and then it will shift it again. Actually, that's a good point. This might return true. Because if start is 0 and end is 0, and we add it together, it's going to give us 0. So maybe say not equal will probably work. And if we leave the while loop, we need to return negative. And there we have it. We have 3, 3, 5, 5, and negative 1. Let's see what happens if I put the less than. Okay. Well, it doesn't give me that. That's weird. Because they're both equal to 0. Why would they not return this? That's interesting. I'm not sure how that part is working. Logically speaking, I feel like this makes more sense because they both start and end are pointing to the same index. We're going to try to add those together, which essentially will equal to 0. So it should return this. So I don't know why that's not doing that part of it, but who knows? I can do a Google search.
I'm not understanding where the issue is. It seems like they were both returning the proper answer.
They are returning a proper answer.
So what's the problem?
Okay, well, the condition to stop this while loop is if start is greater than end. If start is, oh, I think,
Less than.
yeah, it's less than. Oh, you're
Yeah.
right. I see it now. No, okay, it's good. Because the moment that start and end are equal to each other, it won't even come into here. It will just stop the while loop. You're right. Thank you for pointing it out.
I finished the assignment, but I kept getting an error at the end. Initially, I had P1. If P1 is less than index of list minus 1, or len list 1 minus 1, it would exceed the loop. I would get all the answers right, and then it would throw a out of scope error for the list. Like I had exceeded
Index.
the indices, and I couldn't figure out why.
Show your code.
Sure.
There's somewhere in your list is still trying to run the functionality, but it can't because you're trying to access something that does not exist.
So when I had this, well, this is less than list 1 minus 1. Then I would run it. See, I would get these two would return correct, but then when the false would come, it would say, "Hey, you're out of range."
Okay, yeah. So let's look at it. It threw the error when we try to run this one, right?
Mm-hmm.
This bad boy.
Yeah.
So start is 2 and end is 3. It checks those. It does not equal to 0.
Yep.
Negative 2 plus 3 will give you positive 1. So you are comparing not the item in the list, you're comparing the index. You're comparing if P1, which is index 0, and P2 minus 1.
Well, yeah, because I want to move the pointer. I'm saying if these two put together don't equal 0, then move the pointer. And then so move the pointer P1, move it 1 to the right. So now it starts at index 1 instead of 0. If P1 is not less than P2, then subtract an indices from P1 and reset P1 at 0.
Okay.
I think this is where my problem is.
It's definitely here, right? Because on the right here, you're checking if negative 2 and 3, right? If negative 2 is less than 3, but technically you're doing P2 minus 1. So this is, say, 0 less than, well, what is P2? The length of list 1, which is 1, 2, 3, 4, minus 1 is 3. They're saying 0 is less than 3, I want you to increase the index of P1.
Mhm.
So then it moves it to index 1, correct?
Yeah.
Then you compare it, is 1 less than 3 again, which will be true. You increase 1 by 1, so then it becomes 2, -3. Because it never passes this here. It keeps failing, right?
Like it should,
It-
because there's no answer for the. It
Correct.
should return a false or a -1.
Correct. And then what happens is you increase P1 again. So P1 is now equal to 3.
Which P2 should also be.
Correct.
So P1 is no longer less than, so it shouldn't do that. Should go to the else case, which is P2 -1. And
Yes.
reset P1 to 0 and try again.
Yes. What is the length of the list?
3.
3. And they did 3 minus 1.
Well, okay, the length of the list is 4, but -1 is 3.
So 3, yeah. So P1 does not equal. I'm sorry, P1 is no longer less than the length. Because P1 at this point ends up being 3. And you're comparing it to the length of the list minus 1, which ends up being 3. Which ends up being wrong and ends up being false.
As soon as I change this to P2, it works and it's fine. I don't know. I think I'm tired and just not thinking clearly, too. Oh, what did I do? Yeah. Anyway.
It's all good. But do you guys have any questions on the solution that I gave you guys?
No, I feel like I'm not used to doing coding challenges. It's kind of like I forget good habits, you know? And I guess one thing I need to do is kind of think about the logic of it before I even start to even write any code. And what I started doing was I just started coding, just randomly, not without really a plan in place. And I think that's where I got screwed up here. But it's weird. It's like old habits come back, and then it's like we do a bunch of coding challenges. It's like I remember not to do certain things, but then if I'm rusty, I haven't done them in a while. So I feel like that's kind of what happened. I should have had a better battle plan first before I even started coding.
That's okay. I mean, we're new to these algorithms, right? So it's gonna happen. All right, we're gonna finish off these slides, but not completely. So here's a not so great solution of what we just talked about. It starts a nested for loop, right? The outer for loop, it starts some kind of for I in range of the length of the list. It uses the outer for loop to grab the indexes. It grabs I. It starts another for loop, j in range of whatever I is, up to the length of the list again. Notice that the j starts the number after what I is. So if I is the index 1, j will be at index 2. And then it compares those. It adds them together to see if they're equal to each other. So this does something very similar to using pointers, but it uses a nested for loop instead. It uses the index as a way to keep track of what number they're iterating through, which is not too ideal because the nested for loops. And then you have the method that we talked about, which is the while loop. And it uses pretty much everything that I explained, using the while loop left, less than right, adding them together, checking the total if it's equal to 0, if it's greater than or less than, and handles them accordingly. So 2 different ways of doing it. This one's a much better solution. And we're going to stop there just because I feel like we're pretty burnt out. Tomorrow we have sliding window. And the divide and conquer, we'll talk about it. So it's honestly just one assignment for tomorrow. And then we'll jump into searching, sorting, and recursion. So we're right on schedule. What's the date? Today, Tuesday? Jason,
Yeah,
you're muted.
Yeah, so the unique values.py, is that not is that like a different section then? Because I mean that comes right after multiple pointers.py. I mean, does that belong in a different comment
Oh,
solving problem category? The
there's
unique
two.
values. Okay.
Now I believe this goes hand in hand with the multiple pointers.
Okay.
So we'll do these two tomorrow, the first hour, and then we'll jump into searching and recursion. That'll probably take all of the rest of the time on Wednesday, a little bit on Thursday, and then we'll do Python regex and ASCII halfway through Thursday and on Friday, and then we're done. We're not gonna do this pre-work speed run because the pre-work challenges, I don't know what they are now. I think they're outdated, so we're not doing these. But we have this lesson, searching, sorting, and recursion, and then regex ASCII values as well. And then we'll be done with FOP. The remainder of these two lessons are same to kind of how we did these. We're going to talk about the algorithm itself, how to use it and implement it, and so on and so forth. Have you guys heard of regex and ASCII values yet? Okay,
Yeah.
that should be fun. We'll talk about regex. It's going to be an intro course to it, so you can kind of start utilizing it. You're going to need regex for the immersive program. It's going to be very important. It's going to help you kind of set up the email address for the authentication for your user login, so that's going to be good. And then ASCII is just a small introduction to show you how everything has like a numerical value. So like a character, right? Every character that you have has some kind of numerical value that goes to it. We'll talk more about it later on. But that's pretty much the remainder of the class. We're gonna finish common problem solving patterns tomorrow, the first hour. We'll start searching, sorting, recursion on Wednesday. Finish it on Thursday and start Python regex and ASCII, and then we'll finish that Friday. And then after we're done with regex and ASCII values, we'll have a small like Q&A where you guys can ask whatever you want before we start the program, and I will give you my genuine answer. People usually just drill me with questions those days. But that's going to conclude today's class. I'm going to stop the